Thank you very much. Okay, so I hope can everybody hear me? I think the audio is fine. Okay, so the chair here can. Okay, so it's a distinct pleasure to be invited here as plenary speaker, and I have to say I deeply regret I could not make it, but I have a newborn at home that was just born a few weeks ago, and so it didn't permit me actually to come and as planned. But I'm particularly grateful actually of the organizers that they kept my slot. And I would like to mention up front, I very much like in-person meetings. Okay, can you hear me? Perfect. So first of all, I'd like to thank the organizers for inviting me to this venue. I very much regret I could not come actually in person. We have a newborn at home that's just a few weeks old, and it turned out to be challenging to organize the replacements for me at home. But I'd like to thank actually very much the organizers for keeping my spot here and giving me the opportunity to talk about the work we've been doing on next generation integrated photonics. I very much like in-person meetings because of the reason to actually meet people and talk. And so if there is something that that raises your interest in this presentation, then please do email me. I'm very happy to actually follow up and have a conversation about the work we're doing. And I think some of it actually very much also aligns with the community of MEMS that is united here. So I'd like to tell you next 35 minutes is a tour through what I like to call next generation integrated photonics. And before I get started, I'd like to mention also that I'm involved in a few startups, some technology I'll try to highlight today, in particular not just silicon nitride, but also how you can use it to make frequency agile lasers, which we're doing in deep light. And also we have recently founded a new foundry for lithium niobate and lithium tantalate, two materials I'll mention actually in this presentation. And so I'd like to first give an overview actually of really what is a lot of the motivation underlying integrated photonics. And let me start by mentioning that when the laser was invented in 1960 by Ted Maiman, it was called a solution looking for a problem. And I think all of you probably agree that this comment that was made in the 60s is hard to perceive from modern times. In fact, lasers actually allow us to have this very conversation. They're used in optical telecommunications. They're the backbone of data centers. They can be used for next generation perception technologies, FMCW LiDAR. They're used to cool atoms to create some of the most precise atomic clocks that only lose 1 second in the age of the universe. You can use them for OCT, detect chemicals. And lasers actually have been part of more than 50 Nobel Prizes. So the use of coherent laser light is truly pervasive actually in science and technology. But one thing actually that is very striking, and it's very different actually in a community like MEMS that is united here, is that if you look at how lasers are typically manufactured and assembled, in fact those principles actually haven't changed in the last 50 years. And most of the lasers that we use today in numerous applications are still based on legacy schemes that either use kind of optical fibers, okay, so bulk fibers that are assembled by hand, or actually bulk components. And so if one looks at the most compact lasers today, the most compact lasers today that exist actually are based on silicon photonics. That is very compact silicon integrated photonic circuits that guide light that are coupled to 3 5s to create lasers. That has been a very successful technology that transitioned from academic research to industry in 20 years and is now used in data center interconnects, so-called pluggable optics. But what's important to realize is that this very compact integrated lasers actually have not challenged legacy lasers in terms of the coherence, in terms of the power. And that argument can not only be made for lasers, it can also be made for amplifiers or for optical combs. In fact, there's a huge gap between the performance of legacy systems and integrated systems. And why is that? Where does the challenge come from? Why can't you use state-of-the-art micro nanofabrication technology based on silicon to create lasers that are as good as the bulk counterparts? And the reason actually this is not possible has to do with the material itself. So silicon, despite being one of the most studied materials for semiconductor processing and remarkable investments over many decades, it has some fundamental material properties that make it actually very challenging to make high performance optical systems out of this material. And chief among them is the limited bandgap of 1 electron volt that prohibits actually making devices that operate in the visible. It has moreover limited power handling capability, so typically tens of milliwatts. Due to the low band gap, it also doesn't allow to harness its nonlinearity because one suffers from two-photon absorptions. And this may sound very non-intuitive, even using state-of-the-art like global foundries processes, it's challenging to get waveguides with losses that are, say, less than a dB per centimeter. And those factors combined have made silicon a wonderful material for microelectronics, but it has not allowed to make lasers or amplifiers or combs, based on silicon photonics. And so what has happened over the last really 5 years or even last decade is that there's a revolution ongoing in photonic integrated circuits based on new materials. And I'd like to highlight you today in this talk actually some of the advances that my lab has made in silicon nitride, but they're made in many other labs around the world. It's now a foundry material. Following silicon nitride now, there's a wave of new materials that are on the horizon, in particular lithium niobate, lithium tantalate, which I'll briefly touch upon, and also new methods actually of incorporating gain by ion implantation. And this actually wave of developments now makes it possible to close this performance kind of compactness gap that I've outlined. And you can make devices that now are challenging legacy optical systems actually in performance. And so they're not just systems that are smaller, lower power, and more compact, scalable manufactured, but the most important aspect is their performance can be inherently better than bulk systems. And that's a very new development that holds promise also now to translate these technologies actually into applications. And so the first thing I'd like to introduce is the platform that we've been studying, in particular of silicon nitride photonic integrated circuits. And in this presentation, I'd like to tell you, in particular, emphasize how this platform can be combined with MEMS. And I'd like to highlight the very important role actually that MEMS can play in augmenting integrated photonic circuits. So a brief comment about silicon nitride. So optical losses of silicon nitrides have come down by more than a factor of 100 in the last decade. And so starting about 10 years ago, the silicon nitride losses were similar to SOI, like a dB per centimeter. And via new manufacturing techniques, some of which I'll introduce today, you can actually now go down to losses that are only 1 dB per meter. Now this is still far away from the optical losses you have in optical fibers, so the transparency actually would still allow to push losses further down. But this allows new devices to be generated, and I'll highlight a few of them. One can now make, with these very low loss integrated photonic circuits, very narrow line width lasers, so-called chip-scale frequency combs, which I'll briefly introduce. But also it's a platform for photonic quantum computing and many other applications that require long interaction times. Silicon nitride is a material that is well known in the semiconductor industry. It has a band gap of 5 electron volts. It has a moderately high refractive index. It's CMOS certified. Transparency window is from the mid-IR to the visible, and has no two-photon absorption. Plus, it's a space-compatible material. Now, the challenge with silicon nitride, however, has been that this material, when you grow it with LPCVD, so low pressure chemical vapor deposition, which occurs at a high temperature, typically 800 degrees, actually this material forms cracks. And this crack formation has prevented to create thick layers, thick meaning wavelength scale, to create very tightly confining circuits for many years. And it's over the last decade actually that these problems have been solved. And so the way we have, in my lab and also other labs have overcome this is we have introduced a new manufacturing technique. And instead of manufacturing by depositing films and etching them, what you would call subtractive processing, what we have done is we have taken a very well-known material, which is an oxidized silicon wafer, and etched a preform inside that waveguide. And this preform actually hosts the waveguide material. What's the advantage here? The advantage is we do not have to actually etch silicon nitride. We can directly deposit into the preform. We can make stress release layers to avoid actually that cracks propagate. We can then perform planarization, so CMP, place a cladding on top, and make waveguides that are as high as 1 micron without suffering from crack formation. So this technique actually allowed to make now tightly confining integrated photonic waveguides with low loss of silicon nitride. And this technique that we're using here is very similar to the copper damascene process. That's why we call it a photonic damascene process. And it's commercialized with the company Ligentech that I co-founded some 8 years ago, and that provides actually foundry access to this material. Now, so this technique allows to create crack-free silicon nitride waveguides with exceptionally low loss. Also very closely spaced waveguides. You don't suffer from kind of the problem of gap filling, and has brought down the losses by now about a factor of 100 compared to what was possible a decade ago. Now you can make even lower loss waveguides by playing one more trick, which is to take actually the glass preform and heating it up to the glass softening transition. And that way you take out any roughness that was imparted by the oxide etching and create actually exceptionally smooth sidewalls. And this now brought down the losses to the 1 dB per meter level of a photonic integrated circuits, which is about a factor of, say, 100 lower compared to what's done in silicon photonics today. And so, so these meter-long kind of devices are also very compact. So here's an example of such a chip. So it's a 1 cent coin. You see here 2 spirals with 1 meter, which losses of about 1 dB per meter. And due to the very thick nature of the waveguides extending about 800 nanometer, you can make very tight bands, and you can coil up like a meter of path length into just 2.5 by 5 millimeter. Now, so what can you do with these low-loss silicon nitride circuits? And so over the years, these silicon nitride circuits have been used to generate optical frequency combs. I'll briefly touch upon this. And they are kind of one of the leading platforms for this Kerr comb generation, or microcomb generation as it's called. But what's more exciting recently is that they also provide a platform to create actually frequency agile low noise lasers, and also can be endowed with erbium to create amplifiers, and also lasers based on rare earth gains. And so I'll briefly touch actually on these topics. Again, these low-loss nitrides are a platform, and platform for parametric amplifiers, lasers as mentioned, but also can be endowed actually with further functionality like lithium niobate, whereby it's possible to bond this to create hybrid waveguides, which I will not discuss today. They're also a platform that can foray in very different areas that have nothing to do, say, with lasers or optical systems. Integrated photonics based on silicon nitride is now even used in electron microscopes to manipulate electron wave functions. And also here you generate and you benefit from the high power densities you can achieve in silicon nitride, and the nanoscale confinement of the optical light. The material also is a platform for photonic quantum computing because of the kernel linearity. And quantum computing companies like Xanadu or PsiQuantum use silicon nitrides for its low loss, but also for its linearity to generate, for instance, photon pairs. So let me briefly highlight a couple of applications of the silicon nitride circuits. And one of the first applications that this material was used for is so-called optical frequency comb generations, or so-called microcombs. And so optical frequency combs are equidistant optical laser lines that are used in timekeeping and metrology. And the way they are generated is by using a mode-locked laser. So a mode-locked laser will in frequency domain actually produce a series of equally spaced sidebands, so-called optical frequency combs, that can serve actually as a reference and provide absolute frequency synthesis, or it can provide also a way to take a stable optical frequency and to divide it down to the microwave domain, something that's called optical frequency division. And so these optical combs, even though I've only touched really on the surface here, they have been really revolutionary technology that was invented by Ted Hench and Jen Hall, part of the Nobel Prize in 2005. But they're primarily based actually on bulk optical femtosecond lasers. And even today, 20 years later, there's approximately maybe a few hundreds of optical frequency combs that are being used in mostly metrology labs or very well-equipped scientific labs. And so the reach of optical metrology can be much deeper if the technology can be similar to what has been achieved in MEMS, be commoditized by establishing and using wafer scale manufacturing, which will bring down actually the price significantly, but also really allow new applications where compactness really is essential, which is probably true for all the applications in, say, position, time, and navigation, but also in telecommunications as another example. And so I'd like to briefly outline how this can be achieved with the silicon nitride integrated photonic circuits. And these allow to generate so-called microcombs. And so what is a microcomb? A microcomb actually is a device where you generate an optical frequency comb directly by taking a continuous wave laser and converting it inside the microresonator into equally spaced optical frequencies. And this is based on a process called parametric interactions, whereby when you pump actually one of these microresonators, you generate sidebands due to the kernel linearity of the material itself. And so it's a parametric oscillator. And so typically, this is distinct compared to a laser. The threshold force of parametric oscillation scales inversely quadratic with the quality factor. So the higher the Q actually of the optical resonator, the lower the threshold will become. And this is different than a laser where the threshold actually would have a 1/Q dependence. And so having high Q can bring down the threshold dramatically, even for very faint nonlinear effects like these parametric interactions. And so we observed this effect already more than almost 20 years ago in toroidal resonators. And this process can serve as a basis actually to generate optical frequency combs by using cascaded parametric interactions. And so this provides a way to generate optical combs on a chip, but what's really crucial is it can access very large repetition rates, very easily tens of gigahertz, even to hundreds of gigahertz, even to terahertz. And those are fundamentally not possible to access with, say, fiber laser frequency combs. And so this Carichrome platform have really proliferated. So starting with silicon nitride and silica resonators, it's now been observed in almost all the kind of integrated photonic platforms. And not only can one generate these optical combs, but can also produce very short optical pulses that are called soliton, dissipative Kerr solitons. And the way this works is by scanning a laser actually through a resonance of the microresonator. And what happens here is a very complex interplay of nonlinearity and driving and dissipation, by which you first generate a noisy waveform inside the resonator that is a so-called chaotic modulation instability state. And then when you tune right through the resonance actually of the cavity, you enter the bistable regime where you can create so-called dissipative Kerr solitons. And this is manifested by a very striking series of steps, discrete steps that you see in the transmission spectrum of the resonator, which corresponds to a reduction of the number of solitons. So you go from n to n-1 to n-2, and finally you are in a single soliton state where you have a secant parabolic optical envelope. And so these microcombs, maybe viewed more broadly, what's really happening here is that in these resonators, there's 2 degrees of freedom that you have. One is the laser detuning that are plotted horizontally here, and one is the pump power on the vertical axis. And when you look at this, the physics actually of what happens in a microresonator, this is governed by a very simple equation. It's a nonlinear Schrödinger equation, where the nonlinearity accounts for the Kerr nonlinearity, the dispersion accounts for the geometric waveguide dispersion. But then on the right-hand side, there are new terms. There's dissipation and driving and a detuning. And when you take this equation and actually look for its solution, what's very striking is this partial differential equation has regions where it supports chaotic waveforms, so not stationary waveforms. It had regions where it generates solitons and regions where the solitons can breathe. And you can access actually precisely with a laser all these regions and generate these dissipative Kerr solitons. These are incredibly stable attractors of nature. In fact, it's a very general feature actually of driven systems that form patterns. And so this out of equilibrium system actually forms patterns in the form of optical pulses, very similar to chemical reaction creates stripes, or for instance, winds on sand creates actually periodic patterns like sand dunes. So it's a very universal feature of nature actually, if you have a dissipative system with nonlinearity to create very stable attractors. In our case, these stable attractors are very useful because they are optical frequency combs. And these can be in silicon nitride extremely broad. These are very short pulses, as short as 5 optical cycles, that travel inside the silicon nitride resonator that we can model very well, and that can produce frequency combs with spacings of tens to hundreds of gigahertz. And this on the one hand allows to directly synthesize microwaves by detecting the pulse stream, or to use these, for instance, as lines in coherent communication experiments. And so due to this reduction of losses over the last years, it has become possible to now generate these frequency combs with only a few milliwatts of power level, which is about a factor of 1,000 reduction in the last decade. And also it has allowed to combine, first of all, bring down the repetition rates from hundreds of gigahertz to just a few gigahertz. So here's an example of a soliton microcomb that operates directly in the X and K bands, or the microwave bands, and can be used actually to generate low noise microwaves. Now, due to the low threshold, you can also integrate these devices directly actually with semiconductor gain media. And so here what is shown is a 100 milliwatt indium phosphide DFB that's directly butt coupled to a silicon nitride waveguide and resonator. And here you have 2 effects happening. The first is self-injection locking, whereby a portion of the light is back reflected into the DFB and creates a locking effect. This purifies the spectral tone. I'll say something about this in a bit, and creates very narrow line with lasers. But in addition, we can also generate, on top of this dynamics, a dissipative Kerr soliton. So these are very compact soliton generators, and it's this very low loss in the silicon nitride that allows to create a threshold that's comparable and lower than the typical DFB output. So what is the most compact optical comb we can make to date? We can even go one step further, and there's a collaboration with John Bauer's group where we combined actually the DFB laser directly with heterogeneous integration on the silicon nitride indicator photonic circuit. And what is interesting about this result is it shows the immense potential that wafer scale processing has, because here on this 100 millimeter wafer, there are more than 3,000 chip scale frequency combs that are being manufactured, which is a very significant number compared to, say, the fiber lasers that are being, or fiber combs that are being employed today. So it shows that this technology really has a potential actually for being used in applications. And what could some of these applications be? The applications where microcomb shine most is the applications where a large mode spacing is needed. And this can be massively parallel communications or applications like FMCW LiDAR, where you like to have access to individual comb lines, but also spectrometer calibration or photonic computing, again, where you want to have access to individual spectral components of the lines, actually is where this technology can really be used. Now, I'd like to switch gear and talk about work I think that's particularly also interesting to this community united here, which is the combination of integrated photonics with MEMS. And I think it's no understatement to say that one of the most important things for building optical systems is the ability to actually very quickly actuate and tune optical elements. And so here I'd like to share some of the work that I've been doing over the last decade with a group of Sunil Bhave, in which we have combined piezoelectrics with integrated photonics using the stress optical effect. And so I'd like to briefly explain actually what the rationale is and also what new applications actually this can allow. So first of all, very briefly, I think I don't have to be too detailed here for this audience. The material that we have focused on in our initial work is aluminum nitride. And so what is very unique about aluminum nitride? It's a material that's extremely commercial, has a low RF loss tensions. It provides highly linear actuation with very little hysteresis. It's very low power. It has a low dielectric constant, which compensates for some of the lower piezoelectric coefficient, and also has a low leakage current. In fact, you can generate acoustic waves up to gigahertz frequencies with this actuator, and this is also the reason why it's being used actually in cellular phones by the pioneer work of Ruby. And so we have combined these piezoelectric aluminum nitride actuators with photonic integrated circuits, and the actuation principle that we use here is the so-called stress optical effect. So the piezoelectric actuator actually is removed actually from the optical waveguide that carries the optical light. And what is being used here is simply this stress that is generated by the aluminum nitride actuator, which creates a stress optical effect, so refractive index change in the silicon nitride. And so this technique actually allows the stress optical effect allows to tune the optical resonator via the photoelastic effect or photoelastic constant. And so here on the left you see an example of aluminum nitride actuators, in this case rings, donuts, or rings that actually directly actuate the resonators. Now, for the experts, also mentioned the aluminum nitride, of course, has free boundary conditions. So what's really happening here is that the finite Poisson ratio creates an in-plane shear stress that actually causes a stress that tunes the actuator. So what can you do with this? One aspect that we have used this for is to create lasers that are frequency agile. And the way we do this in one of the embodiment is we use a DFB laser, a very compact semiconductor laser, which in itself actually has a very high kind of typically hundreds of megahertz wide free running line width. What we do is actually we inject this laser into a silicon nitride microresonator with very high quality factor and benefit from the technique of self-injection locking. That is to say that in a certain current range, the laser frequency that DFB actually will laser on is not the innate frequency of the laser itself, but rather actually is determined by the back reflected light actually from the external circuitry. And what is interesting and unique about self-injection locking is that it allows to reduce the line width actually of the free running laser. And this is done in proportion to the quality factor actually of the resonator, in fact inverse Q squared. So a very high Q external resonator will significantly reduce the line width. Now, so when you start to tune the laser current, what you will see is a range actually of which the laser frequency hardly doesn't change because it will be locked and pinned actually to the microresonator, and that's the so-called self-injection locking range. Now here, this provides one opportunity. If you now start to tune the resonator with an aluminum nitride actuator, you can create actually a frequency agile laser because in this case, a DFB will follow actually the external modulation. And this can generate actually tuning with quite substantial actuation bandwidth, in this case 2 gigahertz. But importantly, due to use of ALN as an actuator, we can have a bandwidth that can be very substantial, so typically much more than the few tens of kilohertz that bulk piezoelectric lasers would tune. And so let's take a look actually how well these devices perform. So one of the first results we obtained was we looked at the laser line width of these frequency agile low noise laser. And we compare it to the fiber laser, which is a workhorse for optical fiber sensing. And we were very surprised actually that due to this very high quality factor, the integrated silicon nitride self-injection locked lasers can actually operate actually well below the phase noise actually of a state-of-the-art fiber laser as used for fiber sensing. So this provides an opportunity for the first time to create indicator photonics lasers that are not only compact, but most importantly, their performance challenges actually conventional legacy lasers. And this is due to the use of this very low loss circuitry that is based on silicon nitride. The other, and we have commercialized this technology with the company Deep Light, founded 3 years ago. But the importance is not just the line width. What we can achieve with the silicon nitride is, moreover, very, very fast actuation. So what's shown here actually is the response by applying actually a voltage actually on the piezoelectric actuator that we sweep here from 10 kilohertz to say 10 megahertz. And what you can see in gray is that if you have the device just on an optical table, an optical assembly, where the chip is not clamped down, you actually start to see that the piezoelectric actuator is exciting many mechanical modes. And these are the modes itself of the chip. So the photonic integrated circuit, in this case 5 by 5 millimeter. But when we start actually to play tricks like apodization, that's also used actually in wireless technology, out of phase driving, or just clamping the chip down, we can create, as shown in blue, an exceptionally flat bandwidth up to the first H-bar mode, so the first bulk acoustic mode actually of the actuator. That's typically at 17 megahertz. Now, and this is, to compare this with bulk lasers, this is about a factor of 100 times faster tuning. So what we have here is a really unique combination of very fast tuning and exceptionally narrow line width. Now, where can you use this for? One of the applications can be in FMCW LiDAR, which is a perception technology where you chirp lasers in a triangular fashion. You send it out to an object and you beat it actually, the incoming signal with the outgoing signal to generate an RF beat node. And this beat node encodes both the distance and the velocity of the object. And so FMCW is a very interesting perception technology for this reason. As Art Shallow at Stanford used to say, never measure anything but frequency. FMCW maps both velocity and also the distance to a frequency. But it's been compounded by a very stringent requirement on linearity. And with these aluminum nitride actuators, the linearity actually is excellent, less than 0.5% or even 0.1. And you can achieve here, for instance, very simple kind of imaging of objects in the room and also infer their velocity. So this is really one of the directions. This frequency agility can also be extended to other wavelength ranges. Silicon nitride is transparent and invisible. So there's an example here of lasers that operate here in the blue, or even as short as 410 nanometer. This is a collaboration with SRI from PARC, funded by SEMI. And the shortest wavelength laser we made right now with PARC actually is as short as 360 nanometer, actually based on this technology. Importantly, not only lasers, but also we have this ability to frequency actuate using the aluminum nitride actuators. Another variant of this scheme, and to show you how you can use this aluminum nitride, you can not only use ALN to actuate, say, resonators, but also you can also actuate gratings. And the rationale to do that is to make cheaper lasers that replace DFBs, which are typically costly because you use E-beam, with simple RSOAs, external gain chips. And in recent work also by Snehal Bava, we have shown that if you directly actually have a aluminum nitride actuator on top of a simple grating, we can again get very good actuation bandwidth up to well beyond a megahertz, and create very, very compact lasers that in themselves have line width of typically a few kind of kilohertz, but that can become hertz level line width by actually self-injection locking them to long spirals. And so this is an example of an extremely cost-effective device. It just uses a very cheap RSOA, an external grating that is piezo tunable, self-injection locked to a spiral, and this device gives them 4 hertz kind of intrinsic line width. So it shows that we can now, in negative photonics, achieve fiber laser coherence with incredibly small kind of form factor and also low cost of materials. Now, these piezo electric actuation allows much more possibilities also scientifically that I will not have the time to go into detail about. I want to leave you with a sense of it. With Sunil's Barber group, we showed we can actuate not only lasers, but also chip-scale frequency combs, which can be useful, for instance, for FMCW LiDAR. You can not only have one actuator, but several ones, create actually rotating refractive index gratings, which allow you to create actually so-called circulators, so non-reciprocal devices. You can also use these devices to make microwave to optical converters, whereby you use so-called H-bar modes of the bulk, and use acoustic waves to translate optical microwave frequencies to acoustic frequencies back to optical sidebands. And also, as I mentioned, the frequency agile lasers. And so just give you kind of one example of what can be achieved. We can also use actually the H-bar modes of the stack itself, which have a frequency, in our case, free spectral range of about 17 megahertz. And we can use those to create what we like to call piezoelectric optomechanics, where we have an incoming microwave field that is driving via the piezoelectric effect an acoustic wave, which in itself actually is coupled to optical modes, in this case of a doublet resonator. And so what we can achieve here is, if we drive, for instance, this piezoelectric actuator at 5 gigahertz, we couple and we drive this doublet. What happens actually here is that the electrical signals convert to a bulk acoustic wave, which in itself actually is coupled back and scattered actually into a sideband of the optical pump, which is also resonant. So it functions here as a triply resonant transducer, resonant for the acoustics and also resonant actually for the two optical fields that are coupled via the piezoelectric effect. And these devices actually allow us to explore this so-called optomechanical toolbox that I only want to put there and glance over, but the optomechanical toolbox allows us to convert the mechanical excitation to an optical sideband or the optical sideband to mechanical excitation. And this technique actually allows us, for instance, to create devices as shown here, whereby we can actually convert optical sidebands to microwave generation or microwave radiation into optical sidebands. So it functions as a single sideband or single-sided acousto-optic converter, but in contrast to bulk devices, the efficiency actually can be exceptionally high. Now, in the remaining parts, being like 5 minutes, I'd like to highlight briefly two directions of integrated photonic circuits when it comes to new ways actually to establish gain. And so one of the most studied ways to introduce gain in optical media is actually based on erbium doped rare earth doping. And rare earth ions are the workhorse of fiber optic communications, of fiber amplifiers. They have been developed by Sir Henry Payne in '86. And the reason erbium is so attractive is that it has a very long lifetime. The Hund's rule actually it can even give very narrow emission spectra in solid state. It's also a very temperature stable gain medium, and it can be used to actually transmit data because it has negligible interchannel crosstalk. And so due to this very low loss of silicon nitride, what we can do is we can implant erbium directly into silicon nitride waveguides and make active optical waveguides out of this platform. And erbium has one disadvantage. Its cross section is quite small. It has a limited kind of concentration onto which you can dope it. So typically the most gain you can get in erbium is a few dB per centimeter. But given our very low loss waveguides and the ability to achieve a very high overlap of the implanted films actually with the optical mode, as confirmed here by Rutherford backscattering, we can generate amplifiers that have very decent output power. So this is an example of a 50 centimeter long spiral, 2.5 or 5 millimeters long, that we dope with erbium, which actually generates an output power of more than 100 milliwatt. And so that's actually very comparable to what you have, say, in a fiber optic amplifier. And that's really the first time that we can achieve output powers that are comparable to fiber-based bulk devices. It's also part of a new startup, Advatech, that was started from my lab half a year ago. And this provides really a new platform to provide very compact amplification that could, for instance, one day go into pluggable optics for data center interconnect. So what could you do with these devices? One is you can amplify channels that for telecommunications. So here shown in red is our channels generated by an optical frequency comb at a level of minus 30 dBm, so it's not suitable for transmission. But if you run it through one of these erbium doped waveguide amplifiers, you can comfortably generate power levels of several milliwatts, which is efficient for coherent communication experiments. So these are very compact amplifiers that could find a way actually into next generation pluggable optics for interconnects. And this is also something we explored actually with Nokia Bell Labs. But there's more device you can generate. You can not only generate amplifiers, but also single frequency lasers, or in the future, potentially even femtosecond mode lock lasers actually on chip. And to give you one glimpse of such a device that can also be enhanced and also actuated with piezoelectric actuators like PZT or ALN, I would like to give this device. This is an example of a 70 centimeter spiral that is selectively implanted on chip. We have frequency selective elements. And this device actually serves as a tunable erbium doped laser that can cover actually the full CNL band. And so this is the rendering of the device. This is the actual device, actually how it looks like. You can see here the veneerings, you see the green up conversion from the erbium. And this device actually has very good performance metrics, several milliwatts of output power, very high signal suppression ratio, plus actually it's tunable over the, in this case shown here is only a portion of the CNL band, but we have devices where we get coverage actually of both of them. And so also here, these are actuated at the moment still with heaters, but also here piezos can play a key role to actually achieve fast frequency agility. And so this is the circuit layout of the device that we've generated. Now, in the last 2 minutes, let me just say I talked a lot about silicon nitride, which is a very interesting material for making integrated photonics that has very low loss and that can be tuned with piezos. But in fact, there are more materials with even richer physical properties, and those are in particular the ferroelectrics or the oxide perovskites, such as lithium niobate or lithium tantalate. And just very recently, over the last 2 years, it's become possible to also etch very tightly confining lithium tantalate integrated photonic circuits. And the way we've been able to do that, so first of all, why is this material interesting? The key why lithium niobate and lithium tantalate are interesting is because they have very large optical Pockels coefficients. And that's actually why lithium niobate is used as a workhorse for optical communications and for making modulators. And integrated photonics has become possible over the recent years because of the advent of SmartCut that was first developed in 2018 for lithium niobate. Sorry, it was 10 years ago developed for lithium niobate. It was also commercialized for piezo insulators in the MEMS community. And it's only recently that it has been discovered actually for integrated photonics. Now, why is it taking so long for these materials to be adopted in integrated photonics? One of the reasons is these materials are very hard to etch. They are inert typically to fluorine-based chemistry. They don't create volatile compounds. And but what is very interesting is these materials actually can be etched with ion beam etching and using a very special hard mask. And what we've demonstrated is that a hard mask based on a material called DLC, diamond-like carbon, which is a material actually that is used as an as a protective coating for medical devices or razor blades. This material has a hardness of diamond, but it can be deposited very simply by decomposition of methane gas in the reactor. And it serves actually as a superior photomask for materials that are hard to etch, like lithium niobate, lithium tantalate. And using this material, we're able now to generate deeply etched lithium niobate, lithium tantalate waveguides that have losses that are less than 10 dB per meter. So they're also, fairly low loss compared to what could be done just a few years ago. And so we've commercialized this with an open access foundry called Luxtelligence. And we can now generate deeply etched waveguides with loss levels well below 10 dB per meter, while keeping actually very tight band radius. And what can you do with these materials? We just flash through one example here. We can generate ultra broadband optical frequency chromes, electro-optic frequency chromes that span several thousands of lines, which could be used, for instance, for microwave to optical conversion experiments, or actually for low-noise microwave generation using two-point frequency division. And another example, what we can generate is actually very high-speed optical modulators that can run with frequencies up to 100 gigahertz and have driving voltages on the level of just a few volts. And this is possible by using these materials like lithium niobate, lithium tantalate, combined actually with these low-loss etching techniques. Now, one of the last motivations for our research is not just to create high-speed modulators, but also modulators with very low switching voltage. And one application that we foresee in the future, or as possible scientific applications, is to convert actually classical microwave circuitry and superconducting circuits, which is typically done using microwave cabling, and replace microwave cabling by optical cables and very efficient modulators. Very much the same way as data centers now don't run on actually copper cable Ethernet connections, but rather optical links. And for this, what you need are very, very low loss modulators. And the only way to generate these is to actually make very long devices. And you can make modulators with a meter path length in lithium niobate, lithium tantalate on chip that have switching voltages on a level of a few tens of millivolts, which would then allow actually to create these optical transduction lengths. Now with this, I'd like to mention that applications of lithium niobate and lithium tantalate are wide encompassing and cover like many areas that I will not be able to touch, but it's really ushering a new era in integrated photonics. And with this, I'd like to thank all of you for your attention, for coming. I'd like to particularly highlight my collaborators here, in particular Sunil Bhave with integration of piezos. And also like to mention that if you have any questions or if this talk raised curiosity, please do email me. I'm responsive. I would have loved to interact with this community. And finally, also like to mention indicator photonics is making a transition that MEMS was doing 20 years ago. This is early stage. A lot of technologies are just being transitioning to possible markets. We have 3 startups: Deep Light for lasers, Luxtelligence, and Advatech. If you're interested, please reach out to me. We're hiring and would like to shape the future of negative photonics. Yeah, so in the context of microcombs, I mean, these are free-running devices, and so the noise they will inherit is just the noise actually of the system itself. And so in the case of microcombs, this has been very well studied. So if one example, I think even on one of the slides. So for instance, the free-running microcomb, say a 10 gigahertz repetition rate, will have a typical microwave noise that is on the level of minus 120 dBc per hertz at 10 kilohertz offset, which is say like a moderate like RF. You can see them here. So the single phantom phase noise, which is due to the fact that the lines actually are independently have independent noise processes, will come down at about minus 120 at 10 kilohertz offset. And so the best been done today and observed in such microcombs is quite a bit better. So crystal resonators can have phase noise of close to minus 140 dBc per hertz at 10 kilohertz offset. So comparable to say to a state-of-the-art Rode-Schwartz microwave generator. But innately they will always have noise that comes from the laser. That there are various mechanisms actually that will make the microwave pulse stream not completely pure. So thank you for the question. That's absolutely a correct question. So I choose today to show many topics rather than go into one to detail. But this is absolutely the case. So what you actually see on the graph here, you see on the left the waveguide, on the right the waveguide, and if you squint your eyes, you will actually see that the sidewalls are slightly deformed. And why is that? Because in this example here, this was an 800 nanometer thick silicon nitride waveguide that had a loss before implant of about 3 dB per meter. What we have seen is that the implant at very high energies, high meaning here 2 MeV, 2 mega electron volt, actually starts to slightly deform the waveguides. And the only reason that the waveguide still has very low loss lies in the fact that it has a cladding on the right and left that actually provides physical protection during the implants. And we have verified that after the implants, there's about maybe a dB per meter more loss from the implant itself, but it still retains sufficiently low loss. Now, the other way to reduce damage actually is by going to lower energies. Some of the laser devices that we have recently been studying, we have reduced the thickness of silicon nitride from 800 nanometer to just 200, which brings down the energy by about a factor of 4. And there, the implant damage is very negligible. But this was indeed one of the surprises that we found, is that the implant damage on the waveguide itself in terms of optical loss actually is very minor, even at very high energies. Yeah, so the silicon nitride has a band gap of about 5 electron volts, and so and what we have seen actually in this material is that we can still have self-injection lock lasers that operate as short as 370 nanometer. This is unpublished result with Thomas Wundra from SRI Semi in California. So they still operate actually at 370. Now, if you want to push even further into the even shorter wavelength, I think the better material to use actually is lithium tantalate, because lithium tantalate actually is known to be also transparent down to the UV. The band gap is also quite similar. It's right around a bit more than 5 eV, but that's even say more promising material to push even further down. So for integrated lasers right now, the shortest we can do in silicon nitride is 370 nanometer. So the limit of the height, so going back to the Damascene, so the limit of the height right now of the waveguide is simply given by the dimensional or the aspect ratio we choose actually of the openings of the waveguide width to height. And so what we have done in our work is we have created waveguides as high as 1 micron. The problem is if we go more than 1 micron, at some point actually the deposition itself becomes unstable, so it's hard to avoid the crack formation. So up to a micron is what we can comfortably do in this Damascene process. But as I mentioned, the Damascene process is only one part of the low loss. The other part is really the crack mitigation. So every one of these chips, also if you look at commercial chips in Ligentech, you see these checkerboard patterns. So you always need to make sure that you avoid actually the crack formation of the LPCVD nitride on the wafers itself. Yeah, I mean, in theory. Yeah. If you etch all the way through, you always see a. I didn't put in the slides, but we have detailed actually this in papers that we published, very detailed follow-ups from Martin Pfeiffer, who developed the process in my group. In I think some of the reference even here. Indeed, there's a limit also because of the way the conformal nature of the deposition works. That's absolutely correct. But the highest we've done experimentally is 1 micron waveguide thickness for mid-IR waveguides. Yeah, thank you very much. And again, I regret that I could not have discussions, but please, if you have questions, if something raised your interest, please do reach out to me. I'll be very happy to engage. Thank you.